I have done a recording of this video before, but while I was doing that, the battery and my microphone died, so most of the audio is missing. So therefore, I've decided to record this again. Fortunately, I kept everything that I wrote on the board during when I was doing this video for the first time, so I will just go over it with you. So first, I wanted to recall that this notion of span, right? If you have finitely many vectors in Rn, you can look at what is called the span of those vectors. So the algebraic definition is that it is the set of all linear combinations. So you start with finitely many vectors, and you start adding them and applying scalar multiplication, and you get a whole bunch of new vectors. And what you get is called the span of your set of vectors. So if you look in R3, in three-dimensional space, the span will be, it could be just a line, or it could be a two-dimensional plane, or it could actually be all of R3. Right? So this will happen, for instance, if you start with two vectors that are not parallel, their span will be a two-dimensional plane. And then if you take a third vector which is not on that plane, the span will be bigger than a two-dimensional plane. So it will be, then it must be all of R3. So these subsets that are called the span of some vectors, so these are the important subset of Rn from the point of view of linear algebra. So if you look in R3, well, you can say, okay, in this case we get lines and planes. Doesn't seem to be very interesting. And on one hand, this can be true, but on the other hand, we understand lines and planes in R3. So that's a good thing. Yes, planes are, they can be described using some equations. So we know how to describe planes using equations. We know how to study them. So that's actually a good thing. Even though they are just flat surfaces, they don't look that interesting. Maybe if you study eventually multivariable calculus, you will see some lot more interesting surfaces, two-dimensional surfaces in R3. But these can be described using more complicated equations. Okay, so yes, planes in R3 don't look very interesting, but at least they are easier to study. Okay, so, and one can look at, can talk about what are called hyperplanes. So they are the analogs of planes, but inside Rn when n is bigger than 3. And we cannot visualize them, but at least we can study them using linear algebra. So when you take some vectors in Rn, well, it's possible for their span to be actually all of Rn. So a priori, this may not seem to be too interesting because we know Rn already. Okay, so if you look at the span of those vectors, if it is all of Rn, we don't really get anything new. But actually, this is still an important case. Eventually, we will learn about the notion of basis, and we'll talk about basis for Rn. And well, Rn always has what is called a standard basis. So for R3, it will consist of the three vectors that have a 1 and 1 components and zeros and the other two components. So if you look at the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1, you obtain what is called the standard basis for R3. But it is the case that well, the standard basis is, for most purposes, it is good enough, but there are some instances where it's useful to have a different basis for R3. For instance, rotations in three-dimensional space can be represented using matrices, but to study rotations, it can be useful to consider a basis of R3, which is not the standard one. Okay, and that basis will consist of three vectors whose span is actually all of R3. So, well, we'll come back to this notion of basis later. I'm just trying to give some justifications for studying the case when the span is all of Rn. Okay, so that's an interesting case to consider, even though we can already describe Rn as all the set of column vectors with n components, sometimes it's good to have, we need some good set of finitely many vectors to study those, okay? And those vectors, yeah, should span all of Rn in that case. All right, so so we have this following important theorem, right? So if we take k vectors in Rn, so what we should do with them is to form the matrix A that has those vectors as columns. So this is what this notation means, right? So if I have column vectors and I put them all together like this, one next to each other, what we get is a matrix. Actually, one can view a matrix as a row vector where the entries are column vectors. One can also view a matrix as a column vector where the entries are row vectors. So these are the 2 points of views, and they can both be useful. Okay, so we form this matrix, and for actually many problems in linear algebra, if you don't know how to solve it, if you've got a bunch of vectors, many times what you do is that you form this matrix and you row reduce it. Okay, so we have k vectors, they're all columns, and they all belong to Rn. So A will be an n by k matrix, so it has n rows. So far, most of the time, we had matrices that were of size m by n, so m rows and columns. Here it's a bit different, okay? So one has to be a little bit careful. Okay, so the theorem says the following. If you look at the span of these vectors, right, the set of all their linear combinations, if it's all of Rn, so if you can get all the vectors in Rn just starting from these vectors, and then using vector addition and scalar multiplication, then the rank of A must be n. And conversely, if the rank of A is n, then the span is all of Rn. And recall that the rank of A is the following numbers. So how do you compute this? You take A, you put it in row echelon form. Okay, it doesn't have to be the reduced row echelon form, just any row echelon form. And you look at the number of non-zero rows. Okay, this number is what is called the rank. So the rank can never be more than n, which is the number of rows here, okay? So when the rank is maximum, when the rank of A is exactly the same as the number of rows is equal to n, so while in this case, when it's equal to n, then you can conclude that these vectors span all of Rn. So, well, I can explain a little bit why this is true. So if we want to show this, right? So let's say I will prove one direction. So here we have this arrow, this double logical implication. So it means that if this is true, then this is true, and if this is true, then this is true. Okay. It also means that if this is not true, if the span is strictly smaller, then the rank has to be strictly smaller than n. And vice versa, if this is not true, then this is not true. All right, so let's say that we want to understand why if the rank is n, then the span is all of Rn. So to check this equality, what it means is you take a vector b in Rn, and you should be able to see how to express it as a linear combination of these k vectors. So it means that you start with b, and you know b. You have to think that you know b, you know u1, u2 up to u sub k. And you need to find x1, x2 up to x sub k. So what I have here is a vector equation. They are unknown variables, x1 up to x sub k, but the vectors are known. And as I have explained in the previous video, a vector equation is equivalent to a system of linear equations. So I can start with this vector equation, I can write that linear system, and we now know how to solve linear systems. What we do, we form the augmented matrix and we row reduce it. Well, the augmented matrix of the corresponding linear system is this matrix AB. So the matrix of coefficients is the matrix whose columns are these vectors that we are given, and B is the column of constants. Right, so if you want to solve this system, if you want to see if we can find a solution to this equation, well, we would, put this matrix in row echelon form. Well, if we want to find a specific solution, we even want to put it in the reduced row echelon form. But here I'm only interested in whether or not there exists a solution. And for that, it's enough to just put this matrix in row echelon form. So you apply row operation, and actually what you will get will be a new augmented matrix, where the first part would be actually a row echelon form of A. Okay, and then the last column it will change. So I wrote it as B prime, so it means it's a vector obtained from B by applying row operations. So normally it would be a different vector from B. Okay. And now, so if we look at this, we want to see if we can find a solution to that system. So we have to look at this matrix, okay, and see, well, is there always a solution to the corresponding system? Right, so a system doesn't have a solution when, once you put it in the row echelon form, you get an equation of the form 0x1 plus 0x2, etc., all the way to plus 0x sub k equals something that's non-zero. But here it cannot happen, okay, because, well, can we have a row here of the form all a bunch of zeros and then some number which is non-zero, okay? Well, this cannot happen here, okay? Because the rank of A is n, so it means that in this row echelon form of A, there's no row of zeros. All the rows are non-zero, and they all have some leading entry, some leading non-zero entry. Okay, so because of this assumption, if the rank of A is n, it means if you compute a row echelon form of A, it has n non-zero rows. All the rows are non-zero. So here you never have a row like this, where the last entry is something non-zero. Okay, right? So this means that the system has a solution. Okay, because again, if you have a system which is inconsistent, which does not have a solution, when you row reduce the augmented matrix, you will obtain a row like this. Okay, and then you can say right away that there are no solutions. But here this doesn't happen when the rank of A is n. Okay, so this implies that there are no rows like this, so this system is a solution. So this vector equation is a solution, which means that B is a linear combination of u1, u2 up to u sub k, which means by definition that B belongs to the span of those vectors. All right, let me just quickly give you a couple of examples. Right, so the first example was in R3. So we take these three vectors, u1, u2, and u3. Okay, so, well, the question would be, so what is the span of these vectors? Is the span equal to R3 or not? Right, so we've got three vectors, so maybe the span is, it's either a two-dimensional plane or it's all of R3, right? These are not parallel to each other, so the span is not just a line, so it must be bigger. So it's either a two-dimensional plane or R3. Well, we follow this, we want to apply this theorem, so we form this matrix A. We take these vectors and we just put them as columns of some matrix. We row reduce it, so I got this row echelon form. Row echelon forms are not unique, right? So maybe you could start with this matrix, perform some different row operation, and obtain a row echelon form which is a little bit different. Okay, so the reduced row echelon form is unique. Okay, everyone should get the same as long as you don't make any mistake. But for the row echelon forms, they do vary. Anyway, so this is one row echelon form. Okay, and the question is, well, is the rank of A equal to 3? Well, for the rank of A equal to 3 to be equal to 3, this row echelon form should have 3 non-zero rows, but that's not the case. There are only 2 rows that are non-zero. This means that the rank of A is 2, okay, and therefore by that theorem, the span is not R3. It will be something strictly smaller, so it's going to be here a two-dimensional plane. Here's some other example in R4, right? So I've got these 4 vectors, u1, u2, u3, u4. So I can do the same thing. I can form this matrix, just use these column vectors to get a new matrix. Can compute some row echelon forms. I got this one. Okay. If I were to continue and obtain the reduced row echelon form, I would get the identity matrix. Okay, so in this case, we see that this row echelon form has 4 non-zero rows. This means that the rank of A is 4. The rank of this matrix is 4. And consequently, we can deduce from from this theorem, we can deduce that the span of these 4 vectors is all of R4. So, one can deduce actually from this theorem that if k is strictly less than n, so it means that in the matrix A there will be fewer columns. If the number of columns is less than n, okay, or the number of vectors here is less than n, then the span must be strictly smaller than Rn, okay, because the rank of A is going to be strictly less than n. If the number of columns of A is less than n, the rank will be less than n, okay, and therefore the span must be something smaller than Rn. Okay, so in other words, in R3, if you have fewer than 3 vectors, if you have only 2, their span is never all of R3. Okay, which, again, if you think in terms of planes, direction vectors for planes, I think this makes sense. In R4, if you have only 2 or 3 vectors, the span will be strictly less than R4. Okay. It could also be possible that you take 5 vectors in R4 and the span is also strictly less than R4. This can happen. Okay. Having more than n vectors does not ensure that the span is all of Rn. But having fewer than n vectors, it implies that the span has to be a smaller subset, strictly smaller subset than all of Rn.